Alrighty, lads and ladies, welcome back. Let's see what we got here. Yeah, all that stuff. Okay. So we have lately been talking about polynomials, and I'm aware that the last few lectures are a bit on the dense side. Right? We've been talking about dividing polynomials, which is a pretty heady thing to do. It's not at all obvious that that would be so intimately connected with factoring. And today we are going to continue in that trend as we talk about the real zeros or real roots of polynomials. The good news is that really just one kind of new big thing today, and that's a particular theorem that I alluded to last time when we said, you know, where does that hint come from? How do we know what to try and divide by? So we'll get a little bit more practice with the kind of mechanics and that we worked with last time, but with this one extra little thing added in. Let's get that screen share turned on and we can start moving this out of the way. So there we go. All right, here we go. Oh, I see there's something in chat. Yeah, so Pierre mentioned something interesting there. As you may or may not know, this Friday is UF's homecoming. And in their limited wisdom, the calendar committee here at Santa Fe chooses to close our college for their homecoming. So if you want to go to the homecoming parade, you're free to do that. You know, that's a thing. I will be having an office hour despite the college closure. So if you need to see me in office hours tomorrow, if you're planning to see me in office hours tomorrow, that is still going to be an option. One little caveat there, and that's that I do have a particular appointment with one of my students in an honors calc class who's going to be doing a student teaching presentation early next week, and I'll be working with him. But I will have an office hour. It'll just be a little bit limited in its scope, and it'll be the same link as normal, the same time as normal, 1 p.m. Okay, where did all right. So yeah, today we're going to talk about the real roots of a polynomial, and the real prefix there is as a kind of preview to what's coming later, which are complex roots to polynomials, not non-real numbers. I think it would be nice to begin with a little recap of the results so far, at least the main ones. But before we do that, we got to do the thing. So this is MAC1140 section 008, which is a pre-calculus class. And today, I believe, is the 7th of October. Today, we're going to talk about the real roots of polynomials, which is section 3.4. Kind of in preparation for that, I just want to remind you that there are some neat connections between factors, roots, things like this. So I'll say, recall that any polynomial can be written in two forms. So this isn't like the vertex form and standard form thing from quadratics. We're talking about polynomials in general, and polynomials in general don't have vertices. They're more complicated. But there is like an expanded form and a factored form. Let me get this out of the way. And that might be something like p of x equals 2x cubed minus 2x squared minus 28x plus 48. And then the other version is the factored form. And that same polynomial could be written as 2 times x minus 2 times x minus 3 times x plus 4. And I think the thing that I really want to remind you of here is that that lead coefficient is the same in either form. So this, this lead coefficient is the same in both forms. That's maybe not the most obvious thing in the world, although it's not terribly hard to show in general. A proof of it wouldn't be a good use of our class time, but it is a fact worth remembering. So remember, if I tell you the roots, you can write down the factors. But like we saw in that last problem that we did on Tuesday, if you want to uniquely determine the polynomial from the factors, you also need to find that lead coefficient. And it's a useful thing to know that if you're starting with the expanded form and I give you the roots, then you can write down the factors and that lead coefficient will be the same in either one. Also useful when finding the end behavior, right? Because you need to know about the lead coefficient. Is it positive or is it negative when you're cooking up your end behavior? Other main things to remember. Roots tell us about factors. And conversely, factors tell us about roots. All right, and what I mean by that is if p of c equals 0, then x minus c is a factor. And conversely, if x minus c is a factor, then p of c is equal to 0. So there's this kind of duality between factors and roots. And then, of course, you remember from the previous week's lecture that if you know the factors and their multiplicities, and you know the end behavior, then you can sketch a very nice graph of any polynomial function. So our kind of goal, again, through the first half of chapter 3, is for me to give you a big polynomial in its expanded form, and for you to get the graph. And the way you did that, or the way you are going to be doing that in the homework, is by finding the end behavior, and then looking at the factored form to find the local behavior near the roots. Once you have those things, you have everything you need for a nice graph. The second to last problem that we worked on Tuesday, where I did some division, some synthetic division to factor a large polynomial, is sort of archetypal of the type of problem I want you guys to be focused on as we work through this first half of the chapter. And I want to emphasize, as you do the homework, draw the graphs by hand, then pick the graph in WebAssign. So this is similar to when we talked about transformations and I pleaded with you guys to draw the graphs by hand, right? And then match your graph to the graph in WebAssign rather than kind of working backwards and looking at the graphs and trying to guess which one is correct. Unfortunately, in the process of grading the tests, I get a pretty good feel for how many for how sincerely we take that advice, right? So the transformation problems there on the test sometimes went really well, sometimes did not go very well. And you know individually if yours went well or not. And I think the most important thing is that you practice drawing the graphs by hand. Don't just like click through WebAssign until you get it right. I don't want to be cruel and put like a 2 answer or 2 submission limit on the problems in WebAssign, because I don't think that is conducive to good learning. But at the same time, you need to exercise that discipline. Otherwise, the skills will not develop. Okay, so that's enough of me preaching. The second to last problem we did on Tuesday, I gave you a big polynomial and we said factor the thing. And the hint was try dividing by x minus 1. Where did that hint come from? Who knew that 1 was going to be a root of that polynomial? Right? Where on earth could we have gotten that information from? It turns out it's something called Vieta's formulas, or more specifically, a tool called the rational roots theorem, which is the big tool for today that I'm going to share with you. Imagine, you multiply all this out. All right, look at this guy. You multiply all this out. What's the constant term going to be? Well, if I multiply -2 times -3 times +4, that's 24 times the lead coefficient would be 2 is 48, right? So what you see is that every number here that is a root, 2, 3, and -4, are divisors of 48, right? 48 is divisible cleanly by each of those roots, 2, 3, and -4. That's the big thing, is that when you multiply out a bunch of factors like this, the constant term will be the product of the roots and the lead coefficient. But in particular, each one of the roots will divide cleanly this number. So if I give you a big polynomial and I ask you to factor it by using synthetic division, what you're going to do is you're going to use that fact that I just described to come up with a list of possible guesses. And then you're going to use synthetic division to check them one at a time. As soon as you find a root, as soon as you do the synthetic division and get a remainder of 0, which means you found a root, then you will have extracted a factor. And you can kind of begin the process again on the resulting quotient polynomial. So with that said, let me show you the theorem and then show you how to use it. It's actually slightly more complicated than what I alluded to there, but here goes. This theorem is called the rational roots theorem. And I have a funny story to go with this. What it says is, if the polynomial p of x equals, and I'm going to write this out in the general expanded form, so an x to the n plus an minus 1 x to the n minus 1 plus all the way down to a1x plus a0, if that polynomial has any rational roots, then they will be of the form, and there's a bit of notation here, don't be intimidated, be of the form x equals plus or minus little p over little q, where p, little p, divides the constant term, a0, and little q divides an, the lead coefficient. So what this theorem does is, it, given a polynomial, it generates a list of possible roots. And then, if you want to factor that polynomial, what you do is you check one at a time using synthetic division. You run through that list until you find a root. Once you have found a root, you look at that synthetic division, you write down the answer in the form P equals QD plus R, and that will be the start of factoring. Let's do it. So I'll give you a second to hold here. Are there any questions about the notation, what this theorem is saying? We all clear on what I mean by divides? Like 2 divides 6, 3 divides 6, but 4 does not divide 6. All right, here we go. Factoring graph. P of x equals 2x cubed plus x squared minus 13x plus 6. The first thing I would do is find the end behavior, because the end behavior we can see from this expanded form. We know for the graph we're going to need the end behavior. If I was just trying to factor it, we wouldn't need this. The degree is 3, which is odd. The lead coefficient is 2, which is positive. So my end behavior in that goes to notation would be as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to positive infinity, right? The end behavior is down on the left and up on the right. And I don't yet know what's going on in here, but that's what we're going to figure out by factoring it. In order to factor the thing, we're going to use the rational roots theorem. Which means we need to generate a list of P's and Q's, kind of like that old saying about politeness, mind your P's and Q's. So the P's here are divisors of the constant term, and the Q's here are divisors of the lead coefficient. So what numbers divide 6? Give me a full list of divisors of 6, or just any divisors of 6. What do you guys think? What are the divisors of 6?
2 and 3 and 1.
1, 2, and 3, yes, very good. Any others?
6.
6 itself, excellent. So 6, 3, 2, and 1. Okay. 2 is a prime number, so its only divisors are 2 itself and 1. So the divisors of the lead coefficient, the Q's, are just 2 and 1. So my possible rational roots, I'll just say possible root. We'll say it out. Possible rational roots are, we have to take all possible fractions where you've got an element from P divided by an element from Q, and you have to allow for a plus and minus. So here's what I'll do. I'll take all of these over 1 and then all of these over 2. So that's plus minus 6, plus minus 3, plus minus 2, plus minus 1. That's taking every p and dividing it by 1. And then we have plus minus 6 over 2, plus minus 3 over 2, plus minus 2 over 2, and plus minus 1 over 2. And some of these are redundant, right? Some of these are the same number. 6 over 2 is 3. 2 over 2 is 1. So like this guy is redundant. This guy is redundant. So here is my full possible list of rational roots for this polynomial. That's correct. So there's a question in chat, why do the q's have both 2 and 1? Because we're listing not just the lead coefficient and the constant term, we're listing all the divisors of the lead coefficient. So p's are any number that cleanly divides the constant term, and q's are any number that cleanly divides the lead coefficient. So 6 is divisible by 6, 3, 2, and 1, and 2, the lead coefficient, is divisible by both 2 and 1. Any other questions about where this list comes from? This is kind of this is the only new thing today. So it's worth taking some time. I'm sorry, could you repeat that?
You said that the P is all numbers that cleanly divide the lead coefficient, and Q are all the numbers that cleanly divide.
Other way around. P is all the numbers that cleanly divide the constant term, and Q is all the numbers that divide the lead coefficient.
Okay, thank you.
Okay. So in the special case where the lead coefficient is 1, it's like that very first polynomial we looked at where we said, oh, all the roots have to divide the constant term. Okay. So my possible rational roots are 6, plus minus 6, plus minus 3, plus minus 2, plus minus 1, plus minus 3 halves, and plus minus 1 half. I like to start checking the easy things first. So I would say like 1 and 2 are easy things to check. So let's test x equals 1. And remember, the fastest way to test if something is a root is synthetic division. So we're going to synthetically divide this polynomial by the factor x minus 1.
I have a question.
Yes.
Could you also just plug it in?
You could. You absolutely could. And that would tell you whether or not this is a root. But the nice thing about doing the synthetic division is if this is a root, you also get the quotient. So if you just plug in 1 and you find that p of 1 is 0, that's great. You found a root and you know x minus 1 is a factor. But what would the other factor be, right? That would mean we could write p of x as x minus 1 times something, but it wouldn't tell us what the something is. If you use synthetic division, it's every bit as fast, and it tells you what the other factor is. So the synthetic division really is the way to go here. So let's do it. Let's do it. I'll try to convince you that this is the most efficient way. Mathematicians, we're very lazy people. So I promise you, I will never take you down a path that is shittier than it needs to be. So remember how the synthetic division works? I write the suspected root over here. And then I write in here the coefficients of the polynomial that I'm dividing. So the coefficients of p in order are 2, 1, negative 13, and 6. 2, 1, negative 13, 6. And then the way we execute the synthetic division is by, so we're checking to see, I'm responding to a question in chat here, we're checking to see if x equals 1 is a root, right? If x equals 1 is a root, then x minus 1 is a factor. Let me come back here. This is, if p of 1 is 0, that would mean x equals 1 is a root. Then x minus 1 is a factor. That's what this is. So roots and factors come together. So we're testing to see if x minus 1 is a factor, which is equivalent to saying we're testing to see if x equals 1 is a root. So I'm sorry, I'm responding to questions that are coming in DMs here in the chat, but I want to make, they're good questions, so I want everybody to hear them. The question was, do we need to test everything in this list? Maybe, maybe. As soon as you find one that works, though, you stop. So, if I ran through how many things are here, 1, 2, 3, 4, 5, 6 times 2 for the plus and minus, there's 12 possible things to check here. It's possible that I run through 11 of them before finding one that works. Now, that would be shitty, but it's possible. But as soon as you find one that works, we stop. So I'll show you how this works. Of course, the synthetic division goes just like it did before. You bring down the 2, and then 1 times 2, we multiply those and write the answer over here. 1 plus 2, you add those is 3. 1 times 3 is 3, write that over here. Negative 13 plus 3 is negative 10. 1 times negative 10 is negative 10, plus 6 is negative 4. So what we've just learned here, this is the remainder. And remember, by your remainder theorem, that means that's the value of p of 1. So x equals 1 is not a root. This has not been successful. So we move to the next guy. The next guy I would like to test is 2. So I write 2, and then the coefficients 2, 1, negative 13, and 6. And the synthetic division is actually faster than plugging in. That's the nice thing, because you don't have to raise anything to any powers. So again, bring down the 2. 2 times 2 is 4. Plus 1 is 5. 2 times 5 is 10. Plus negative 13 is negative 3. 2 times negative 3 is negative 6. Oh, shit. That does add to 0. So we get a remainder of 0. And just like when you learn to do long division in second grade, if the remainder is 0, that means the things cleanly divide each other. In other words, once we find one that works, we'll stop what we're doing and move to the kind of next step. It depends on whether, how large the polynomial is, whether we'll need to continue doing synthetic division. I'll show you some examples of both. So this remainder is 0, which by the remainder theorem means p of 2 is equal to 0. So x equals 2 is a root, which means x minus 2 is a factor. Now, you could, in theory, continue running through your list of possible rational roots until you've found everything that works. But remember, polynomials can have irrational roots also. So it's possible that this polynomial has roots that aren't on this list. They're just irrational numbers. So we don't want to do that. Also, we don't want to fucking sit here and go through all these. What you do now is you write the polynomial. P of x in the form P of x equals Q of x times D of x plus R of x. This is why we learned that. R here, the remainder is 0. So this piece is going to be 0. So what we've learned is that P of x, which is 2x cubed plus x squared minus 13x plus 6 is equal to q times d. Well, what is q? Here's the coefficients of q. So q is 2x squared plus 5x minus 3. And what is d? What was I dividing by? I was dividing by x minus 2. So what you see here is that we've successfully started to factor this polynomial. Yeah, that's correct. We only need to find one that works. Once we find one that works, we kind of stop and reassess the situation. So now that I've found a root, right? I found that x equals 2 is a root, which means that x minus 2 is a factor. And the quotient is 2x squared plus 5x minus 3. So if I want to continue factoring this, all I have to do is factor this quadratic. And that's not all that hard, right? Remember, we know how to factor quadratics. You'd use your AC method on this. And what you would find is that 2x squared plus 5x minus 3 is 2x minus 1 times x plus 3. And then x minus 2 is x minus 2. I can show you kind of off to the side how that works, right? Remember the AC method? The 2x squared plus 5x minus 3 has a times c equaling -6 and b equaling 5. So I need to find those two numbers that multiply to -6 and add up to 5. Those would be +6 and -1. So I'd write this as 2x squared plus 6x minus 1x minus 3, and then factor by grouping. So this is 2x times x plus 3 minus 1 times x plus 3. And then you have 2x minus 1 times x plus 3. That's where the other two factors there came from. So once you find a number that works, you write down the result from that division, right? And you write it down in this form, the QD plus R form. Since R is 0, because that's what it means to say you found a root, you found one that works, you'll just have Q times D. D is the thing you were dividing by, x minus 2, and Q is the quotient that you get when you do that division, the thing whose coefficients come out from the synthetic division right here. And if you're lucky, the thing that you get here, Q, is something that you know how to factor more easily. You don't have to go back to using synthetic division. If this were a hard to factor polynomial, like degree 3 or higher, then you would need to start back over with the synthetic division on this guy. But here, quadratics, we know how to factor quadratics. This is not hard. Any questions on how I got the fully factored form of this polynomial? I guess if we're being very picky, we're not quite in the fully factored form yet. Remember what I said about the fully factored form having the same lead coefficient as the original? Well, here the original has lead coefficient 2. This doesn't have a 2 out front the way my example at the start of class did, because this is not in the form x minus c. If I want to go all the way here, I can force factor a 2 out of this, and it will become x minus 1/2. And then the other guys stay the same, x plus 3, x minus 2. So this down here would be my fully factored form. So again, I want to pause for just a second and see how comfy are we with this? Any questions about how we arrive at that bottom purple line? Okay, so if I want to draw my graph, I just use the factors and the end behavior. Each one of those factors is multiplicity 1. So I have a root over here at -3. I have a root at positive 1/2. And I have a root at positive 2. So these are 3 points I know are on the graph, those x-intercepts. I also know that my end behavior is down on the left and up on the right. The question was, why do I pull this 2 out? Well, I wanted to write this in the form some constant times x minus c, right? I wanted to write this in that form that we said at the very beginning is the fully factored form. Either one would be fine, truthfully. I would not complain. If you told me this is the factored form, I would accept that. I'm just demonstrating that 2x minus 1 can be written as 2 times x minus 1/2. That we can put any polynomial into this form, a constant times each of these factors like that. So now the multiplicity of each of these roots is the power of each of these factors. Each of them are multiplicity 1. So our roots were -3, +1/2, and 2, and their multiplicities were all 1. So each one of these roots, we're not going to bounce or do any S-curvy stuff. We're just going to cross. Since my end behavior on this side is negative, I know at this root, I have to cross from below to above, right? There's 2 possibilities. It could go like this, or it could go like this. It has to be the first one because this end behavior arrow here has to connect to it. Similarly, now I know I'm coming out of this guy going up, so I have to arrive at this next guy going down. And since I leave this guy going down, I have to arrive at this guy going up. Neat, right? So the graph altogether then has to look something like this. Has to look like this. Now, do I know how tall this hill is? No. Do I know how deep this valley is? No. But I have a pretty good picture here. This is a pretty good picture. I'm happy with this. And if you drew it with this hill a little lower or this valley a little deeper, that would be fine. The important thing is that it has the right number of maxes and mins. It has the right roots. It has the right local behavior near the roots, and it has the right end behavior. We can compare with Desmos. So I'll type in the expanded form. X cubed plus x squared minus 13x plus 6. And if I zoom out a little bit, boom, boom. Really not bad, right? We can scale our y-axis and make it look even better. Right. Pretty good stuff. Okay, so this is our goal, right? This is our goal, is to arrive at this graph. Are there any questions about how I got this graph?
Where did the multiplicity 1 come from for each of them?
Remember the
No, that
multiplicity.
was last week, but
I'm sorry, could you repeat that last part?
I said I think that was last week, but I was just wondering where the 1 came from.
So the multiplicity is the power of the factor, right? And since each,
okay.
yeah, so none of these factors were like squared. I didn't have x minus 2 times x minus 2. I just had 1 copy of x minus 2. And the same is true for the others. So it's just the power of the factor.
Okay, this factor is not the, okay, thank you.
Yeah, it's not too bad. All right, the next one, we're going to do this again. The next one I'm going to show you is slightly more complicated. There's just going to be a little more work to do because it's a higher degree polynomial. This time I may not draw the graph, I may just factor. P of x equals x to the 4 minus 5x cubed minus 5x squared plus 23x plus 10. Oh, you ready? Here's story time, right? I said I have a funny story for the rational roots theorem. So me personally, I was bad at factoring, like really bad at factoring. I remember up through pre-calculus, I never really learned the AC method. I could factor quadratics only if the lead coefficient was 1, like in college algebra and at the start of pre-calculus. And when I learned this rational roots theorem, I was like, holy shit, now I can finally factor anything, right? I'd been afraid of factoring since like 8th grade, failed algebra 1. I didn't have told you guys this, failed algebra 1 3 times in high school. Well, once in 8th grade and then 9th and 10th grade also. I was really bad at this shit. So when I learned this theorem and I was finally starting to get it, I got so excited that I went home. I was like, I can factor anything. And I wrote down just a random polynomial, right? Just something like this, only I picked the coefficients at random. And I was like, all right, I should be able to do this. Generated my very large list of P's and Q's, started checking the synthetic division. And after about an hour, I realized that none of them worked. How is that possible? How is it possible that even though I checked every number from the rational roots theorem, I didn't find any roots? What must have been true about that polynomial?
Are all the roots irrational numbers?
Yes, all of the roots were irrational. In fact, if you write down a random polynomial with coefficients from, say, -50 to 50, the probability that any of the roots will be rational is about 5%. 95% of those polynomials will have all irrational roots. So just a silly, funny story. I wasted a bunch of my time, but then eventually I did learn something from it. Okay. So we employ our rational roots theorem. Of course, I'll be picking the problems carefully. You won't run into that, at least not in the homework or on the tests. But just something to be aware of. Most polynomials don't have any rational roots. So I need to generate a list of P's and Q's. P's are divisors of the constant term, and Q's are divisors of the lead coefficient. So the divisors of 10 are 10, 5, 2, and 1. 10 is a semi-prime, so it has 4 divisors. Q is 1, right? Or sorry, the lead coefficient is 1. The only divisor of 1 is 1. So my possible rational roots are plus minus 10, plus minus 5, plus minus 2, and plus minus 1. I start by testing x equals 1. So I write 1, and then the coefficients of P, which are 1, -5, -5, 23, and 10. And I bring down the 1. 1 times 1 is 1. -5 plus 1 is -4. 1 times -4 is -4. Plus -5 is -9. 1 times -9 is -9. Plus 23 is 14. And 1 times 14 is 14. Plus 10 is 24. So this is not 0. So x equals 1 is not a root. And we move on. Just working my way up the list, test x equals 2. So I write 2, and then the coefficients of P, 1, -5, -5, 23, and 10. Bring down the 1. 2 times 1 is 2, plus -5 is -3, times 2 is -6, plus -5 is -11. 2 times -11 is -22, plus 23 is 1. 2 times 1 is 2, plus 10 is 12. So again, Remainder is not 0. So x equals 2 is not a root. Next up would be 5. So I write 5, and then the coefficients 1, -5, -5, 23, and 10. Bring down the 1. 5 times 1 is 5, plus -5 is 0. 5 times 0 is 0, plus -5 is -5. 5 times -5 is -25, plus 23 is -2. 5 times -2 is -10. Hallelujah, we got one. So x equals 5 is a root, which means x minus 5 is a factor. I'm glad. All right, so x minus 5 is a factor, and here's the coefficients of the quotient. So what we've learned is, I'm just going to write, because p of x is so big here, I'm just going to write p of x equals my x minus 5, I'll write that out front, times the quotient polynomial. Now, p of x was a degree 4 polynomial, so the quotient here is going to be degree 3, 1 less, and his coefficients are 1, so that's 1x cubed, plus 0x squared, I'll write it, minus 5x, minus 2. All right. So what's different between this and the last problem? What's different about the quotient here compared to the quotient from the last problem?
This one has exponent.
Yeah, this one, they all have exponents, right? But this one is a degree 3 exponent, right? This is a degree 3 polynomial. So the last time we did this, the quotient polynomial was quadratic. And we know how to factor quadratics always. We never need the rational roots theorem to factor a quadratic polynomial. Here, though, the cubic polynomial is a little harder to factor. So this is giving me an opportunity to answer an earlier question. Do we need to check everything in the list? The answer is no. Once you find something that works, you write down the result of the division, and then you work on trying to factor this new guy. And if this new guy is something you know how to factor, that's great. If it's something we don't know how to factor, then we need to start back over with the rational roots theorem. So now we apply the rational roots theorem to this guy, to x cubed plus 0x squared minus 5x minus 2 to keep going, right? I don't need to keep going with my original list. I just keep going with the list for this guy, and I work just with this guy. There's no reason to keep working with the whole big polynomial p, because I've already kind of started to break it down. And if I want to break it down all the way, it suffices to just break this guy down. So his list of p's and q's, smaller than the original list. P are divisors of -2, which are just 2 and 1. Q here are divisors of 1, which is just 1. So his possible rational roots are just plus minus 2 and plus minus 1. And what's more, I already checked positive 1 and positive 2, right? If positive 1 or positive 2 were roots of this guy, then they would also have been roots of the original. And I know they're not roots of the original because I already tested them, and I found that they were not. So I can start back over with -1 or -2. let's test x equals -2 for this guy. So I'd write I'll do it over here, -2, and then the coefficients of this quotient, which are 1, 0, -5, and -2. Bring down the 1. 2 times -1 is -2. Add -2 to 0, you get -2. -2 times -2 is +4, plus -5 is -1. -2 times -1 is +2. Add that to -2 and you get 0. So this tells me that x cubed plus 0x squared minus 5x minus 2 is equal to x plus 2 times the quotient from this, which is x squared minus 2x minus 1. Therefore, we're still not quite done. P of x, my original polynomial, is x minus 5 times this guy. And this guy is x plus 2 times this guy. And now the only thing that's left over is a quadratic. And I always know how to factor these. If we're lucky, we can factor it with the AC method. So here a times c is -1 times +1 is -1. So I need two numbers that add up to -2 and multiply to -1. But the only numbers that multiply to -1 are +1 and -1. And those do not add up to -2. So this guy doesn't factor nicely. How do you factor a quadratic if you can't use the AC method? How could I find the factors for x squared minus 2x minus 1?
Quadratic formula.
Very good, right? The quadratic formula will always give us the roots of a quadratic. Once you know the roots, you know the factors. So to this guy, I apply the quadratic formula. This is kind of our worst case scenario, but we can do it. The roots here will be negative, I'll write it out, -b plus or minus the square root of b squared minus 4ac all over 2a. So what is that? That's -2, which is 2, plus or minus the square root of b squared minus 4 times a times c. So that's b squared is 4 minus, I'll write it out, minus 4 times -1 times +1 is minus -4. And this is all over 2a, which is 2. So let me continue this over here. So Victoria asks, could we attack this with the rational roots theorem? The answer there is you could try, but if the rational roots theorem was going to work, then you would have been able to factor it by hand. So right, being able to factor with the AC method is equivalent to saying this quadratic has rational roots. So because this quadratic does not factor with the AC method, its roots must not be rational, which means if you attacked it with the P over Q stuff, it wouldn't work. You could check everything and you would find nothing works. So we really do need the quadratic formula at this point. So what is this? This is 2 plus and minus the square root of 8 over 2. And the square root of 8, remember 8 is 4 times 2. So the square root of 4 times 2 is the square root of 4 times the square root of 2, which is 2 times the square root of 2. And all of that is over 2. You can factor the 2 upstairs and you get 1 plus or minus root 2 over 2, and then you can cancel those 2's. So you get 1 plus or minus the square root of 2. So those are my two missing roots. I'm not going to take this away. I'm just going to move it up a little. So by the quadratic formula work, x squared minus 2x minus 1 is x minus 1 plus root 2 times x minus 1 minus root 2. And those little parentheses inside there are very important. So as with quadratics aren't special in this sense, any polynomial, once you know the roots, you can write down the factors. I know the roots, so I've written down the factors. And they're a little bit weird looking, sure, but whatever, it's all right. It is good to know about how big these are, right? If I did want to graph this, I would want to know what are these numbers, because, you know, they look weird. The square root of 2 is a nice thing to know. It's about 1.4. So this is like 1 plus 1.4, which is about 2.4. And this one is 1 minus 1.4. So that would be 1 minus, that would be about negative 0.4. So if we were going to graph, that would be good information to have. But we're not, we're just trying to factor. And now we are genuinely done. So hence, P of x is x minus 5 times x plus 2 times x minus 1 plus root 2 times x minus 1 minus root 2. That is the fully factored form of this big, scary fourth degree polynomial. I know that this is a fairly involved problem, so I would like to take a second and make sure we're all super duper comfy, or as comfy as we can be. I'll zoom out a little bit, try to get as much of this working here at the level where we can see it. Here's most of the good stuff. All right. Questions on any of these steps? Okay, I'm not going to draw the graph here, but I do think it's worthwhile to take a look at the graph in Desmos. So let's do that and try to confirm or deny our work. X4 minus 5x cubed minus 5x squared plus 23x plus 10. Here it is. Let me check what these roots look like. So there's the root at negative 2. He's coming from the x plus 2 factor. Here's the root at positive 5. He's coming from the x minus 5 factor. And the other two roots are those weird irrational ones, right? See, it's about negative 0.4 and positive 2.4, which is just what we said, right? 2.4 and negative 0.4. So this looks how we would expect it to look. It's an even degree polynomial with a positive lead coefficient. So the arrows would go up on both sides. And the roots are what we think they are. And we cross at each one because they are multiplicity 1 roots. Not bad. Not bad at all. Okay, last call for questions on this. Okay. I would like to do one more. And this one's going to be a little scary. This is a degree 5 polynomial. Fact of the polynomial p of x equals 2x to the 5 plus 5x to the 4 minus 8x cubed minus 14x squared plus 6x plus 9. And it's more or less the same stuff. I am going to use my rational roots theorem. Which means I need to cook up little p and little q. The divisors of 9 would be my little p's, and those are 9, 3, and 1. The divisors of 2, the lead coefficient, are just 2 and 1. So my possible rational roots are plus minus 9, plus minus 3, plus minus 1, plus minus 9 halves, plus minus 3 halves, and plus minus 1 half. We have not checked a fraction like this, so I'd like to show you how to check a fraction. So let's start with 1 half. It goes the same way. It goes exactly the same way. So I'm going to write the suspected root and the coefficients of p, which are 2, 5, -8, -14, 6, and 9. I bring down the 2. 1 half times 2 is 1. 1 plus 5 is 6. 1 half times 6 is 3. -8 plus 3 is -5. And here's where we're going to have to start carrying around some fractions. -5 times 1 half is -5 halves. And now you need to be a little bit careful with your arithmetic. So I need to add -14 to -5 halves. 14 is the same as 28 over 2, right? So this would be -28 over 2 plus -5 over 2, which is -33 over 2. And then when I multiply that by 1 half, I get -33 over 4. And I need to add that to 6. 6 is the same as 24 over 4. 24 over 4 plus -33 over 4 is -9 over 4. And -9 over 4 times 1 half is -9 over 8. I guess I should have left a little more space here. -9 over 8 plus 9. Well, if I write 9 as a ratio over 8, 9 times 8 is 72, minus 9 is 63, so this is 63/8. And since this is not 0, we know x equals 1 half is not a root. So I know that arithmetic there got a little bit unpleasant, but it's still manageable, right? It's not that bad. And this is just one of those places, like I've been saying all semester, we really have to get comfortable with fractions. There's no escaping it. So I hope that that was not too bad for you guys. Normally I would have started with 1. Let's go to 1 next. So I have 1, and then the coefficients 2, 5, -8, -14, 6, and 9. One times 2 is 2. 2 plus 5 is 7. 1 times 7 is 7. Plus -8 is -1. Times +1 is still -1. Plus -14 is -15. Times 1 is -15. Plus 6 is -9. Times 1 is -9. Plus 9 is 0. Hey! So that remainder is 0. So x equals 1 is a root. Which means x minus 1 is a factor. And the quotient, the other factor, is going to come from these coefficients, like always. So what I've discovered here is that p of x is equal to x minus 1 times the polynomial whose coefficients are listed here. I started with a degree 5 polynomial, so these will be the coefficients of a degree 4 polynomial given in order. So that's 2x to the 4 plus 7x cubed minus x squared minus 15x minus 9. Now I still have a degree 4 polynomial to work with, right? I still need to factor this big honker. So I generate a list of p's and q's for him. Since his constant term and lead coefficient are the same as the constant term and lead coefficient of the original, it's the same list of p's and q's. All right, so it's actually the same list here. So I'm just going to keep moving through that list. In the interest of saving time, I'll tell you, obviously, I know what's coming here. I'm going to check 3/2 next. So now we continue working with this guy, with the 2x to the 4 plus 7x cubed minus x squared minus 15x minus 9. And again, his list of p's and q's are the same as the original, so I don't need to generate a new list. But when I do my synthetic division, I'll be doing it with this guy, not with the original, right? So I am still saving myself some work by having extracted this factor. Because I don't want this to take all day, I'm going to check the next guy that I know works, which is 3/2. So I write 3/2, and then the coefficients of this guy, which are 2, 7. I'm going to give myself a little more space. -1, -15, and -9. Bring down the 2. 2 times 3/2, that's 3. 7 plus 3 is 10. 10 times 3/2. Again, you want to get comfy with this. So that's like 1/2 times 10 times 3. So that's 5 times 3 is 15. 15 plus -1 is 14. 14 times 3/2 is the same as 3 times 7 is 21. 21 plus -15 is 6, is that right? 6 times 3/2, again, cancel the 2. So that's 3 times 3, which is 9. Oh, thank goodness. And that's going to add up to 0. So this guy equals 0. So x equals 3/2 is a root, which means x minus 3/2 is a factor. So what I have so far is p of x equals x minus 1 times 2x to the 4 plus 7x cubed minus x squared minus 15x minus 9, which by what we just did is equal to x minus 1 times x minus 3/2 times the quotient here, which is 2x cubed plus 10x squared plus 14x plus 6. Oops, sorry, here we go. I'll hold here just for a second. Okay, this guy has a different constant term. So here I will generate a new list of P's and Q's. My P's will be divisors of 6, which are 6, 3, 2, and 1. My Q's are 2 and 1. So the things I could test here would be plus or minus 6, plus or minus 3, plus or minus 2, plus or minus 1. And then 6 over 2 is 3, it's already there. 3 over 2, we can check, might show up again. 2 over 2 is already there, 1 over 2. 1 over 2 we already checked. I'll write it because it's a part of this list. But I know I don't need to mess with 1 over 2 because 1/2 wasn't a root of the original, so it can't possibly be a root of this guy. 3 over 2 we've seen is already a root, but that doesn't mean he couldn't show up again. So in theory, we might have to check him. And then these guys, we could exclude anything from this list that was not on the original list. That's a neat fact. So I want to point that out. Remember, if 6 was going to be a root of this thing, then it would have had to have been a root of the original. But 6 wasn't on the list for the original. So I'm going to cross off the ones I don't need to check here. I don't need to check 1/2 because I already checked him. I don't need to check 6 because he wasn't on the original list. Is there anything else here that I can say I don't need to do? Yeah, what about the 2, right? 2 wasn't on my original list. So I've got plus minus 1 and plus minus 3. All right. Let's do something we haven't done yet. Let's check -1. So I'll write -1, and then the coefficients of this guy, which are 2, 10, 14, and 6. Bring down the 2. 2 times -1 is -2, plus 10 is +8, times -1 is -8, plus 14 is 6, times -1 is, yay, -6, so this is 0. So this is 0. So x minus -1 or x plus 1 is a factor. So where am I now? I've got p of x equals x minus 1, x minus 3/2 times, I'll just go ahead and write the result here. It's x plus 1 times, what do we get from this? That's 2x squared plus 8x plus 6. And now I'm down to a quadratic. I can try to factor that. We can actually bring a 2 all the way out of this thing, right? Every piece here is divisible by 2. And I'll write that 2 all the way out front. So this is 2 times x minus 1 times x minus 3 halves times x plus 1 times x squared plus 4x plus 3. And then x squared plus 4x plus 3. How do I factor this guy? Well, two numbers that multiply to 3 and add up to 4 are 3 and 1. So finally, this is 2 times x minus 1 times x minus 3 halves times x plus 1 times, what did we say? 3 and 1, right? So this is x plus 1 times x plus 3. Here is your fully factored form. There's only one thing I would do beyond this. Does anybody see anything else I can do to kind of write this in a way that would be helpful for graphing?
X plus 1 is squared in this.
Very good. Yeah, that's exactly it. So John nailed it. I've got an x plus 1 times x plus 1 here, which is the same as x plus 1 quantity squared. So this is 2 times x minus 1 times x minus 3 halves times x plus 1 quantity squared times x plus 3. And so if I wanted to graph this, I would list the roots and their multiplicities. The roots are 1, 3 halves, -1, and -3. The multiplicity of 1 is 1 because this power here is 1. The multiplicity of 3 halves is also 1. The multiplicity of -1, he's the interesting guy, that's 2. And the multiplicity of -3 is 1. So I could now draw a nice graph of this, right? The 2 I factored out from here. So remember, after I get to this line, my goal is to continue factoring whatever's left over, which is this quadratic. And kind of the simplest factoring trick we have is there a common factor? So I could have written the 2 right in front of the quadratic here. I could have written this 2 right in here. But it's nice to kind of stack these up and put any constants out front. So I just moved the 2 all the way out front because everything here is being multiplied. So we can put it wherever we want. And it is the lead coefficient, right? If we compare to the original polynomial, there's a 2 for the lead coefficient. So I expect if I write the fully factored form, that I should have a 2 out front, and I do. Alrighty, I think that's where we're going to leave it for the day. Maybe I'll just take a quick look at this graph, and we can again verify that we didn't mess up too badly. So this was 2x to the 5 plus 5x to the 4 minus 8x cubed minus 14x squared plus 6x plus 4. Here it is. Oh wait, did I write something wrong? Mouse? Oh, 9. Yeah, sorry. All right, so here's the multiplicity 2 root at -1. We bounce off the graph. Here's the -3, here's the 1, and here's the 1.5 or 3 halves. And we could easily have drawn this graph, maybe not perfectly, but we could have drawn the graph that has the right end behavior, roots, local behavior near the root. So this is it. This is about as deep as we're going to go with the synthetic division stuff. So next time I'm going to talk a little bit about complex numbers. We're out of time, so I won't start there. John, there's a question.
Yes, quick question, sorry. I was wondering, when you define the possible rational roots for the last function, you said to delete the one that were not on the original list?
Yes. Yep.
Okay. So
yeah,
any
because if a number was a root of this guy, then automatically it would have had to have been a root of the original guy.
Okay.
So anything on this list that's not on the original list can go, and anything that's on this list that I've already checked and found does not work can go. One common mistake, I'm glad you mentioned this, because one common mistake is people assume if they've tested something and it did work, then they don't need to test it again. That's not true. So it's possible that way back here, I could have started by testing -1, and I would have found that -1 worked. But since -1 shows up with a multiplicity of 2, I could have tested it again at this level and found that it worked again. So yeah, at this stage here, we can cross out, or anytime you're doing a second or third rational roots list, you can eliminate or delete anything that you've already checked does not work, and you can eliminate anything that wasn't on the original list.
Okay, and also retest the one that we tested before in case
Yeah.
it worked.
Yep,
Okay, thank you.
sure. And then I saw a little notice from John there. Did you have a question also? Maybe Zoom was just being glitchy. All right, so next time we're going to talk about, oh, sorry, go ahead. Yeah.
I said no, I don't have a question.
Okay, cool. So next time we're going to talk about complex numbers, right? Starting with like the square root of -1, and we're going to find that they are badass. They're really cool. And once we know a little bit about complex numbers, we can kind of say the whole game for polynomials. I'll be able to give you what's called the fundamental theorem of algebra. And then we will be done talking about polynomials, and we'll move on to talking about rational functions. Once we finish talking about rational functions and rational inequalities, we will be ready to take test 2. So we're actually pretty close to test 2. And I just like to keep that in your brains. Alrighty, this is where I'm going to leave you guys for today. There is going to be a new homework popping up. It will be due next Tuesday at the start of class. It's going to be this stuff. And if you need help with anything, I am going to have an office hour tomorrow, although it's going to be a little bit not normal because I'm working with somebody for a special project, and another office hour on Monday. So that's it from me, guys. Take care.
Have a good one. Thank you.
You too.